Think about something you do every day. Maybe sliding in your socks on a smooth floor. Or, hitting the brakes on your bike, maybe a bit too fast. There's this invisible force that's always there fighting against that movement. And here's the really interesting part. Fighting that force doesn't just slow things down, it actually makes things hot. Sometimes really, really hot, like glowing hot, or even hot enough to start a fire. So that brings us to our big question for this deep dive. What is this invisible force that's always resisting you? And why does fighting it sometimes turn simple motion into, well, heat?
Welcome to the deep dive. Yeah, today we are getting into those sources all about friction. You could call it the fiery force. Our mission is pretty clear. We want to figure out exactly how this resistance, this friction, transforms energy. And we'll connect that idea to stuff you see every day, maybe engines, maybe sports, all sorts of real-life systems.
Right. And the core idea we're unpacking today is that friction isn't just annoying, something that gets in the way. It's actually a huge player in energy transformation. It takes the energy of motion, the stuff you can see, and it converts it almost instantly into something you usually just feel thermal energy or heat.
Okay, let's break it down. Starting with the basics, what the sources call the invisible resistor. Friction. It's fundamentally a contact force,
Contact force meaning.
meaning it only happens when two surfaces are actually touching, rubbing together. And its main job, its only job really, is to resist motion between those surfaces.
Okay, resists motion. Got it. But how strong is that resistance? Does it change?
Absolutely. And that's key for anyone designing anything that moves. The research points to two main factors determining friction's strength. First one is surface texture, how rough or smooth the surfaces are.
Like sandpaper versus glass.
Exactly. Rougher textures mean more points of contact, more interlocking on a tiny scale. That means more friction. Smooth surfaces, less friction. The second factor is the force pressing the surfaces together. Think about pushing a book lightly across a table versus leaning on it hard while you push.
Yeah. Much harder when you press down.
Right. More force pushing them together equals significantly more friction. It ramps up the resistance.
Okay, that makes intuitive sense. But here's something interesting we found in the materials. Friction isn't just one single thing, is it? There are types.
That's a really important point the sources make. They distinguish between static friction and kinetic friction. Static friction is the force you need to overcome just to start something moving. And it's always the stronger one.
Like trying to push a really heavy sofa, it takes that huge initial effort.
Precisely. You push and push, maybe grunt a little,
Yeah.
and then suddenly it starts moving. Yeah. And it feels, well, easier to keep it sliding.
Okay, so once it's moving, that's different.
Yes. Then you're dealing with kinetic friction, or sliding friction. And it's usually quite a bit weaker than that initial static friction you had to beat. Knowing this difference is super important, especially in engineering, because overcoming that initial static friction is often where a lot of energy gets, well, let's say used up.
Used up.
Hmm.
Or maybe just changed. Which brings us right back to the heat question. Why does rubbing things together, fighting that friction, make them warm?
Exactly. That energy doesn't vanish. It just changes form. When friction acts between surfaces, the mechanical work you're doing, the pushing, the rubbing, the effort, that energy is directly converted into thermal energy.
Heat. How does that happen? Like down at the tiny level?
It's pretty cool, actually. At the microscopic level, the atoms and molecules on the surfaces that are rubbing together, they get jostled around. Friction forces them to vibrate much faster, much more energetically. And that increased vibration, that jiggling of molecules, is thermal energy. That's what we perceive as temperature going up. You're literally making the atoms wiggle faster.
Wow. So the organized energy of me pushing something forward, kinetic energy, gets scrambled by friction into this messy, disorganized energy of vibration thermal energy. The energy is conserved, it just becomes heat.
Perfectly put. And the sources gave a great kind of extreme example. Car brakes.
Oh yeah, race cars.
Right. Imagine a race car slamming on the brakes from, say, 200 miles per hour. Those brake pads clamp down on the rotor, and they have to convert an enormous amount of kinetic energy into heat, like instantly.
And you actually see it. Those rotors glow bright red or orange. That's the friction doing its job, turning motion into visible heat.
And you don't need a race car to feel this. We actually pulled a quick challenge from the sources for you to try right now.
I want to experiment. Cool.
Yeah. So if you can, just pause for a second, get your hands ready. Now rub your palms together really fast and push them together pretty hard for about, say, 15 seconds. Go.
Yeah.
Feel that resistance. That's the friction you're working against. Keep going. Almost there.
Okay. N. Stop. Now just hold your palms slightly apart. What do you feel? That warmth, right? That heat.
That's it. That's tangible proof of the energy transformation. You use mechanical energy, the motion of your hands, you worked against friction, and boom, you instantly converted that work into thermal energy, into heat.
No magic involved, just physics in action.
So, since friction is basically everywhere, unavoidable,
Yeah, you can't escape it.
right? The real challenge for engineers, for inventors, for anyone making anything is how to manage it, how to control it. Sometimes we need more friction, sometimes we need way, way less.
Okay, let's talk about that. When would we want more?
Think about safety and control. The soles of your shoes, for instance. They're designed specifically with materials and patterns, treads.
To grip the floor.
Exactly. To maximize friction between your shoe and the ground. Without that high friction, walking would be like trying to move on ice, slipping everywhere. That grip lets you push off, stop quickly, change direction.
Makes sense. And wanting less friction.
Well, think about things designed for speed or easy movement. Skis on snow.
Or maybe like an ice skate blade.
Perfect example. You want minimal friction there, so you can glide smoothly and quickly with less effort. Low resistance equals high speed. It's all about tailoring the surfaces and the interaction for what you want to achieve.
It makes you wonder, what if we could have zero friction? Would that be amazing?
Maybe not. We actually rely on friction for stability in ways we don't even think about.
Like what?
Like holding this pen or tying your shoelaces. Even just sitting in a chair requires friction to keep you from sliding off. Without it, things wouldn't stay put.
So
It might be
maybe
total chaos.
Okay, maybe zero friction isn't the goal then. But thinking about maximizing friction, that leads to one of its most ancient and frankly incredible applications.
Ah, you mean fire making.
Yes! Using friction to start a fire. How cool is that?
It really is. And one source dives into this. It seems almost magical, but the science is pure energy conversion, just like we've been talking about. When you rub two sticks together very quickly and with pressure, you're doing mechanical work.
Just like rubbing your hands, but way more intense.
Exactly. You generate enough friction, enough resistance, that the thermal energy builds up rapidly. The temperature of the wood dust created at the contact point rises and rises until it gets hot enough. The science says dry wood fibers typically ignite around 200 degrees Celsius, or about 400 Fahrenheit. So by rubbing fast and hard enough, you're converting your muscle energy into enough heat to hit that ignition point. Add some oxygen from the air and the wood fuel, and you get fire.
Wow. Just simple rubbing, mechanical work, generating enough heat to trigger a chemical reaction. That's fundamental.
It really is. Which brings us neatly to the big picture in engineering and technology. Friction is this double-edged sword. It's totally essential for so many things we rely on.
Like walking, gripping things, stopping cars.
Right. But it's also a constant headache in anything with moving parts.
How so? What are the downsides?
Well, the big ones are wear and tear and energy loss. Friction physically grinds down surfaces over time. Think about engine parts, gears, bearings, they wear out because of friction. And maybe even more importantly, friction means energy is wasted.
Wasted. How?
In any machine, from your bike chain to a giant industrial motor, some of the energy you put in to make it go is constantly being turned into heat by friction instead of doing useful work.
Wait, so even if I'm riding my bike perfectly smoothly, some of my pedaling energy is just turning into heat in the chain and the axle.
That's exactly it. It makes the machine less efficient. You have to put in extra energy just to overcome that internal resistance. It's like an energy tax you always have to pay.
Okay, that's a bummer. So engineers are constantly fighting this energy thief. How do they do it? How do they reduce friction when they don't want it?
The number one weapon against unwanted friction, especially in machines, is lubrication. Using lubricants.
Like oil or grease?
Precisely. Oil, grease, specialized fluids.
Yeah.
They do something really clever. They create a super thin film, a layer, between the moving surfaces. This fluid layer physically separates the solid parts. So instead of metal grinding directly on metal, the parts are sliding past each other on this slippery layer of liquid.
So they're not really touching anymore.
Effectively, no. Or at least the direct solid-on-solid contact is drastically reduced. And that massively cuts down friction, which means less wear and less wasted energy as heat.
That separation layer is key. Okay, but what about when engineers want friction, like you said, for tires or brakes?
Then they do the opposite. They design components specifically to maximize friction. Take tires again. They're not just smooth rubber donuts. The specific rubber compound chosen, the complex tread pattern with all its grooves and blocks,
All designed for grip.
all meticulously engineered to maximize the contact area and create high friction with the road surface. Especially crucial in wet conditions or when you need to stop fast. It's about generating safe, controlled traction.
So you can actually test this stuff yourself, right? The sources mentioned something about comparing materials.
Yeah, it's a simple idea, but reinforces the concept. You could just try sliding different objects across different surfaces at home or in class. Like try sliding a rubber eraser across a piece of paper. Then try sliding maybe a smooth plastic block across the same paper.
And you'd feel the difference in resistance.
You definitely feel it. The eraser would likely have much higher friction. You can even try rubbing them quickly and see if one feels warmer. It directly connects what you feel, the resistance, the heat, back to those core ideas. Surface roughness and the types of materials interacting.
Okay, great. So as we wrap up this deep dive on the fiery force of friction, let's quickly hit the two main takeaways we've explored today. The big ideas to remember.
First and foremost, it's that fundamental energy transformation. Remember that friction is the physical process that consistently converts kinetic energy, the energy of motion or mechanical work, into thermal energy, which is heat. Disorganized energy. You felt it in your hands.
Right. Motion into heat. Got it. And the second big takeaway.
It's the duality. Friction is absolutely essential. We need it to walk, grip, stop, even make fire. It makes modern life possible. But it's also a constant problem in machines, causing wear and tear, making things less efficient by wasting energy as heat. So, controlling it, adding it where needed with things like tires, reducing it where it's harmful with things like lubricants, that's a huge part of engineering.
Okay, so here's a final challenge for you, the listener, to take away from our dive today. Think about a system you know that uses friction. Maybe it is those car brakes we talked about, the pad pressing on the rotor, or maybe something simpler, like striking a match on a matchbox.
Now, picture that system in your mind and try to mentally label the three key things we discussed. First, identify the actual surfaces that are in contact, the ones rubbing together.
Okay, surfaces.
Second, pinpoint the direction of motion. Which way are things moving or trying to move?
Direction, yeah.
And third, visualize where the heat energy is being generated because of that friction, that resistance between the surfaces.
Surfaces, motion, heat. Applying what we learned.
Exactly. From the very first wheel to the most advanced robots, figuring out how to manage friction has been central to almost every invention. So now that you understand this connection between motion, resistance, and heat, look around you. Can you spot a system, maybe something you use every day, that seems like it's struggling, or maybe even failing because there's too much friction that isn't being controlled?
And if you spot one, what kind of fix would you try? Would you add a lubricant, try to make a surface smoother, maybe use a different material altogether? Think like an engineer?